Tectonic earthquake. This is the most common type of earthquake on Earth, and it happens because of the way the planet is built. The outer layer of the Earth is broken into massive pieces called tectonic plates, and these plates are always moving, just too slowly for anyone to feel on a normal day. When two plates grind against each other, pull apart, or collide, the pressure builds up over time until something gives way. That release of energy travels through the ground as seismic waves, shaking everything on the surface above it. The scale of destruction depends on how much pressure had built up and how close the rupture point is to populated areas. Most of the world's major earthquakes fall into this category, including the devastating 2011 Japan earthquake that triggered a massive tsunami and reshaped the country's entire approach to disaster preparedness. Volcanic earthquake. This type of earthquake is directly connected to the movement of magma beneath the Earth's surface. When a volcano becomes active, molten rock pushes upward through cracks and channels underground, and that movement creates vibrations that can be felt for miles around. The ground above an active volcanic system is essentially responding to pressure changes happening deep below it. These earthquakes are usually smaller than tectonic ones, but they can occur in rapid clusters called earthquake swarms, sometimes hundreds of small tremors in a single day. Scientists monitor volcanic earthquakes closely because a sudden increase in activity is often one of the first warning signs that an eruption may be coming. Before the 1980 eruption of Mount St. Helens in the United States, a swarm of thousands of small earthquakes gave scientists just enough warning to begin evacuating the surrounding area. Earthquake. Underground spaces are not always stable. When the ceiling of a cave, mine tunnel, or underground cavity gives way, the sudden collapse sends a jolt through the surrounding rock and soil. These earthquakes tend to be small and localized, but inside a mine, they can be extremely dangerous, causing cave-ins that trap workers deep underground. Some collapse earthquakes happen naturally in limestone regions, where water has carved out hollow spaces over thousands of years, slowly weakening the ground from beneath without any visible sign on the surface. Others are the direct result of human activity, particularly in areas where mining has removed large volumes of material and left the surrounding rock without adequate support. Explosion earthquake. Any large explosion can produce seismic waves, similar to those of a natural earthquake. Nuclear weapons tests conducted underground are a well-known example of this. When a nuclear device detonates beneath the surface, the shockwave moves through the earth in a way that seismographs around the world can detect and measure. The pattern of waves produced by an explosion differs slightly from those of a natural rupture, and scientists have developed tools to tell them apart. This is actually one of the ways governments and international monitoring agencies detect secret weapons testing from thousands of kilometers away. Large conventional explosions from construction, demolition, or industrial accidents can produce the same effect on a much smaller scale, creating brief but detectable ground shaking in the surrounding area. Induced earthquake. Human activity does not just cause collapse earthquakes. Certain industrial processes can trigger much larger earthquakes in areas that might not otherwise experience them at all. The injection of wastewater deep into the ground, which is a byproduct of oil and gas drilling operations, is one of the most studied causes. When large volumes of fluid are pumped underground at high pressure, they can reduce friction along existing fault lines and allow those faults to slip in ways they would not have done naturally for a very long time. Parts of the United States, particularly Oklahoma, saw a dramatic and well-documented increase in seismic activity after wastewater injection became widespread. Areas that had recorded almost no significant earthquakes for decades began experiencing magnitude 5 and above events on a regular basis. Shallow earthquake. Not all earthquakes are equal in terms of depth, and depth makes an enormous difference in how destructive a quake turns out to be. Shallow earthquakes occur within the first 70 kilometers of the Earth's surface, and because they are so close to the ground above them, their energy does not have much distance to spread out before it arrives. The result is intense, concentrated shaking at the surface. Buildings absorb the full force of the energy with very little natural dampening along the way. Many of the most destructive earthquakes in recorded history have been shallow ones. The 2010 Haiti earthquake, which killed over 200,000 people and flattened much of the capital city, had a depth of only about 13 kilometers, placing it firmly in the shallow category and contributing directly to the catastrophic level of destruction. Intermediate earthquake. These earthquakes originate between 70 and 300 kilometers below the surface. At this depth, the energy has considerably more rock and earth to pass through before reaching the surface, which generally means the shaking is less violent directly above the epicenter. However, However, intermediate earthquakes can still be felt across very wide areas because the waves travel through denser, more intact rock that carries vibration efficiently over long distances. In some cases, an intermediate earthquake can be felt clearly in a city hundreds of kilometers away, while people closer to the epicenter notice only mild shaking. This unusual pattern can make them confusing to experience, with reports of strong tremors coming from places that appear to be far from where the event actually occurred. Deep earthquake. Some earthquakes occur at extraordinary depths, between 300 and nearly 700 kilometers below the surface. At these depths, the rock is under such immense pressure that scientists once debating whether earthquakes could even occur there, since the conditions seem to prevent the kind of brittle fracturing that causes most earthquakes. The shaking that reaches the surface from a deep earthquake is usually much weaker relative to its actual energy, though the event itself can be enormous in raw terms. The 2013 Sea of Okhotsk earthquake, which occurred at a depth of around 600 kilometers, was one of the deepest and largest ever recorded. Despite its massive energy release, it caused relatively limited surface damage compared to what a similarly powerful shallow earthquake would have produced. Megathrust earthquake. This is the most powerful category of earthquake that exists on Earth. It happens at subduction zones, where one tectonic plate is being pushed beneath another along a boundary that can stretch for hundreds or even thousands of kilometers. As the descending plate drags downward, the two plates lock together due to friction along an enormous fault surface. Over decades or centuries, stress accumulates along that locked zone until it finally ruptures all at once. When that happens, the energy released is almost incomprehensible in scale. The 1960 Valdivia earthquake in Chile, the most powerful ever recorded at a magnitude of 9.5, was a megathrust event. So was the 2004 Indian Ocean earthquake, which generated a tsunami that struck coastlines across multiple countries and killed over 200,000 people in a matter of hours. Tsunami earthquake. This is a specific and particularly dangerous subtype of earthquake that produces a tsunami far larger than its magnitude would normally suggest. The name refers not to the tsunami itself, but to the type of rupture that causes one. These earthquakes tend to occur on shallow, gently sloping fault zones near the ocean floor, and they release their energy slowly rather than in a sharp, violent jolt. Because the shaking at the surface is relatively mild, people in coastal areas often do not feel alarmed. There is no obvious warning. Then, the ocean behaves in ways that give little time to react. The 1896 Sanriku earthquake in Japan is a historic example, where a moderate amount of shaking was followed by a tsunami that reached heights of over 30 meters and killed more than 20,000 people. Aftershock. Once a major earthquake strikes, the ground rarely settles immediately. The main rupture redistributes stress along the fault and onto nearby sections of rock, and those areas begin adjusting to the new conditions through a series of smaller events. Each of those adjustments is an aftershock. They can range from tremors too small to feel to earthquakes powerful enough to cause serious additional damage on their own. After a major event, aftershocks can continue for weeks, months, or in some cases, years. One of the greatest dangers of aftershocks is that they strike buildings and infrastructure already weakened by the main quake, turning structures that survived the initial event into collapse hazards. Emergency workers and rescue teams often have to operate in areas where the ground continues to shake unpredictably for days after the main disaster. Foreshock. Sometimes, before a major earthquake, a series of smaller events occurs along the same fault. These are called foreshocks, though they can only truly be identified as foreshocks after the main earthquake has already happened. At the time they occur, there is no reliable way to distinguish them from ordinary minor earthquakes that will not be followed by anything larger. Scientists have studied foreshock patterns extensively in the hope of finding a consistent signal that could be used to predict an incoming major event, but results remain inconsistent across different regions and fault types. Some major earthquakes are preceded by clear foreshock sequences, while others strike without any detectable warning activity at all, making foreshock-based prediction one of the most difficult unsolved problems in seismology. Swarm earthquakes. In some locations, earthquakes do not follow the usual pattern of a main shock followed by aftershocks. Instead, a region experiences a large number of similarly sized earthquakes clustered together over days or weeks, with no single dominant event standing out from the rest. These are called earthquake swarms, and they are particularly common in volcanic regions and along certain types of fault systems influenced by underground fluid movement. Yellowstone in the United States experiences swarms storms regularly due to the intense hydrothermal and volcanic activity beneath the surface. In 2017, over 2,000 small earthquakes struck the Yellowstone region within a 3-month period, drawing significant public attention. Most swarm earthquakes are small and cause no meaningful damage, but they provide scientists with valuable information about the state of underground systems that cannot be observed directly. Silent earthquake. This is one of the more unusual entries in earthquake science because a silent earthquake releases energy slowly enough that it produces no shaking that humans can feel at all. Also called slow slip events, these episodes involve tectonic plates moving past each other over days, weeks, or even months, rather than in a sudden, violent rupture. They are entirely invisible without specialized instruments. Researchers first confirmed their existence in the early 2000s using GPS sensors capable of detecting millimeter-scale ground movement. Silent earthquakes are now known to occur regularly along many of the world's major subduction zones, including the Cascadia Zone off the coast of the Pacific Northwest in North America. Understanding them matters enormously because some scientists believe slow slip events can transfer stress onto locked fault sections, potentially bringing a major rupture closer. Induced seismicity earthquake. This type does not fit neatly into the natural world, and that is precisely what makes it worth understanding on its own. Induced seismicity refers specifically to earthquakes caused by large-scale human activities other than wastewater injection, such as the filling of massive reservoirs behind dams. When an enormous volume of water is held in place by a dam, the sheer weight of it presses down on the rock below and changes the pressure conditions along existing fault lines. The Koina earthquake in India in 1967 is one of the most cited examples, killing nearly 200 people in a region that had not historically been considered seismically dangerous. It occurred just a few years after the Koina Dam reservoir reached its full capacity, and the timing led researchers to establish reservoir-induced seismicity as a recognized and studied phenomenon in earthquake science.